Hi, everyone. Hi, everyone. Hopefully, y'all can hear me this time. Sorry for being late. I went to the wrong class, to the wrong Zoom session, because I'm just that awesome. Come on in, everyone. If you have any questions, go ahead and ask. Class is supposed to already be started. Like I said, I'm late here because I was diligently waiting for you all in the wrong Zoom. Can someone type to me, let me know that you can hear me? I figure you seeing my lips move is enough for you to know that I'm attempting to talk. Yeah, you can hear me. Good. Thank you. Appreciate that. So, anybody have any questions before we get cracking? We don't really have that much to do. I just want to sort of recap where we're at and then show you sort of the skeleton of what I need you guys to know about chapter 15. But right now, we've essentially finished chapter 14. There's a little bit of odds and ends that I need to touch up on there and then jump into 15. So, any questions? I sent out an email this morning. Everybody should know that, in fact, all the practice tests and online tests are up now. Right now, you have something called Test 8, Chapter 11, 14, and 15, and then it says EC sort of, which means extra credit, sort of. So what that is basically I'm increasing the number of online tests that I drop the lowest grade for from 1 to 2, and I just introduced another test. So technically, you could just take a 0 on that, and it would be exactly the same as if the test was never offered. But I do not recommend you doing that. In fact, I not only do I recommend you not doing that, I recommend you do this and have it done well before your final. Because it will be helpful in preparing you for the final. That's the most accurate assessment of what chapters 14, 15, and 11 have on them in the final. So definitely recommend you take it. If you don't, like I said, it won't necessarily affect your grade, but the lowest grade that you have for your online test will remain. Still no questions? Got another student coming in. All right. Okay, so I'm gonna go ahead and turn to share my screen so we can recap what I was mentioning to you. So what we've learned is I guess you could sort of call it a paradigm. Basically, there is a type of differential equation you guys have learned. It's called a linear homogeneous second order differential equation that we also call the simple harmonic oscillator equation. And we actually derived it for a simple harmonic oscillator, which is basically a mass hanging on a spring, or actually more correctly, it should really be considered a mass attached to the end of a string that's mounted on a horizontal, that's mounted horizontally against a vertical wall and on a frictionless surface. The mass M is initially, before we start any motion necessarily, could be put at a relaxed position. Since it's frictionless, it's going to be put at the relaxed position for the spring. That position corresponds to x equals 0. And then if I pull it away from the spring, that'll be positive x. And if I push it towards the spring, compressing the spring, that'd be a negative x. So the origin's right down through the middle of the mass when the mass is in the equilibrium spot for the spring. And we can start it off any number of ways. We can start it right there at x equals 0 and give it a pluck. That'll send it into motion. If we pluck it to the left, that would mean it's plucking it in the negative x direction. If we pluck it to the right, that would mean we're plucking it on a positive x direction. That would give it, in principle, some initial velocity that maybe we can know. Maybe we work out the details of F equals ma with someone plucking it. We do the calculation, determine basically how fast it will reach in the limited time of contact, and that would give us our velocity at t equals 0. And if I really did strike it at x equals 0, then that would also tell us that the initial position x of 0, in other words, x of t equals 0, is 0, 2. That v0 is equal to some, 2 meters per second or negative 1.4 meters per second. That's an initial condition, as is x of 0 equals to 0 is another initial condition. So what I'm trying to say with this first equation here is there is our archetypal simple harmonic oscillator differential equation. It's second order because it's got a derivative of the second order, in other words, a second derivative. And it's linear because if you find a solution x1 and you find another solution x2, you can take x1 and multiply it by a constant, and then take x2 and multiply it by a different constant, and then add those two together, and those two would be a solution for this differential equation. That's what makes it linear. And it's homogeneous because the other side of the equation is 0. Okay. What we discovered was that a solution to this is x is equal to a cosine omega t plus phi, where omega has to be the square root of k over m. And as I wrote in red, you also need two initial conditions. This is called the simple harmonic oscillator. And notice the hallmark of the differential equation is you can have a number times the second order derivative plus, again, another number, just a pure number, not a function of t or a function of x. So you can have another number in front of x by itself, and then that's equal to 0. That is the hallmark of a simple harmonic oscillator. So if you look at the simple pendulum, we had a little arc length s for an angle theta, and the pendulum had a length L. So that arc length s, if you measure theta in radians, is just L times theta. So s is equal to L times theta. And if we assume theta is small, then sine theta is approximately equal to theta. So instead of m d2s over dt squared equals negative mg sine theta, I can replace the s with L times theta. Theta is a function of time, but L is a constant. So that becomes L d2 theta over dt squared. The sine theta becomes theta, and I pull the negative g sine theta to the left-hand side. So I get L d2 theta over dt squared plus g theta equals 0. Which, again, I usually choose to write no coefficient in front of the second order derivative, in which case you get d2 theta over dt squared plus g over L times theta equals 0. That, again, is in the form of the simple harmonic oscillator. So you know the solution would be theta equals, I could have written a there, but we normally write theta 0. And cosine omega t plus phi. But in this case, omega is the square root of g over L. As you can see, it's the square root of the coefficient of the function that you're solving for. The function we're solving for is theta. And if you look in that last form where I wrote SHO, that function is preceded by g over L. So the square root of g over L is the omega. Again, you need two initial conditions to really work out what phi and theta 0 are. If we try the physical pendulum, you see that you get, this is the rotational analog to Newton's second law. We get I times alpha, but alpha is the second order derivative of theta with respect to time. So we get I times d2 theta over dt squared is equal to negative mgh sine theta. That's supposed to be the torque. That's the only torque on the system. So notice it's force mg times lever arm h. And then there's a sine theta that takes the component of the force. The force was originally mg pointing down, but we take the component of the force that's parallel to the, or anti-parallel, either one you want to consider it, to the increasing or decreasing theta. And to do that, you have to multiply it by sine theta. But again, if we let sine theta be approximately equal to theta because it's a small angle, then we get d2 theta over dt squared plus mgh over I times theta equals 0, which has, again, the solution theta equals theta 0 cosine omega t plus phi. But in this case, omega is equal to the square root of m times g times h over I, where I is the moment of inertia of the physical pendulum about the axis that it's rotating. I also made a note that the omega is technically equal to 2 pi f, and f is 1 over the period, so you could also say omega is equal to 2 pi over the period. Again, you also need 2 initial conditions for this equation to be completely solved. Anybody have any questions on that? So that's an ongoing problem, but every time you see this type of differential equation, you've already got it solved. It's kind of boring in the sense that you don't have to do any work, but it's also exciting in the sense that I have a solution for essentially an infinite number of problems. And that's what the simple harmonic oscillator gives us, is a solution for an infinity of problems. So I'm going to go with another one, and this one's called the damped harmonic oscillator. And we've worked with it a little bit, but I'm going to start from scratch just so everybody knows what we're talking about. So we're going to take Newton's second law of motion, and that is m times d to, oops, I don't like my d there, m times d2x over dt squared. So that's our ma term from F equals ma. We're going to imagine a spring. So Hooke's law applies. So we have a force negative kx, and the negative tells us that the force always acts in the opposite direction of the stretch, which is key. That's why you have to have that negative. But we can also say it also is subjected to a force, some constant b times the velocity, but the velocity is dx over dt. So those are the forces that are acting on it. I can take time to divide through by m, and then I'm going to put all the differentials and all the functions on the same side. So I'm going to get d2x over dt squared. Now I'm going to put it in order of descending derivatives. So I have to pull the b dx dt over for the first time. So I'll say plus b dx over dt. That's again b times the velocity. And then plus, there's something I'm leaving off. I'm going to write it back in a second though. Plus k times x. All that's equal to 0. But remember, I divided through by m. So there's an m here and an m here. So this one's called the damped harmonic oscillator. So this equation, no matter what the actual physics of the problem is, this equation is referred to as the damped harmonic oscillator. Damped harmonic oscillator. Okay. It has a solution of the form x is equal to a e to the negative gamma t cosine omega prime t. Now your book does that without the plus phi. You can add the plus phi. I prefer to have the plus phi, but your book's doing it consistently without the plus phi. Okay. So it feels to me like I really need the plus phi, because it looks like I only have one unknown that I can tweak, and it's a second order differential equation, so I technically need 2 unknowns. So that's why I continue to put the phi. But the main thing is you need to know that's the solution. And now I'm going to show you how to do what I just did above. What I just did above in those first, in the second and the third simple harmonic oscillators, is I had worked out exactly what omega is. So in this case, I need to work out exactly what gamma is. And what I'll tell you is the easiest way to do that isn't necessarily putting this god awful beast in there, because that's a really ugly function to take the derivative of, because it's got a product rule that you got to apply, all that good stuff. But I can tell you where it came from. If you took a differential equation class, for instance, in differential equations, they would have said something along the lines of this. Let's say, let x equal some a times e to the rho t, where e is an exponential. Okay, that means dx dt, which for ease of notation, we put a single dot over it, and that's determined to be the derivative with respect to time. So x dot is the same thing as dx dt. But we can see that that turns out to be rho times rho times a e to the rho t. And then our second derivative, which would be x double dot, is equal to rho squared a e to the rho t. So now if I plug all that into that differential equation right here, what I get is, and notice, by the way, the second derivative has a e to the rho t in it. The first derivative has a e to the rho t, and the x as a function of itself has a e to the rho t. I'm going to factor that out right now while I'm doing this. So I'm going to plug them in to the differential equation that I just underlined, which is this guy right here. And what you're going to see is I get rho squared plus, in this case, I have b over m rho plus k over m, all that multiplied by a e to the rho t has got to equal 0. And this has to be true, must be true for all t. Since that's the case, then we know that rho squared plus b over m rho plus k over m has to be 0. And that looks like a quadratic equation. So we end up getting rho is equal to negative b, which would be negative b over m, plus or minus the square root of b squared. That'd be b over m squared minus 4 times a, which is 1, times c, which is k over m, all that divided by 2 times a, which is 2 times 1. I can change that into negative b over 2m plus or minus. Now I'm going to take that 2 that's in the bottom. Notice I've already dealt with it in the first fraction by putting it in the bottom of b over m. Now I'm going to force that 2 in the bottom to go inside the square root. That means it's going to become a 4 in the denominator. So I'm going to write this as the square root of b over 2m quantity squared. So notice you now have b squared over 4m squared, which is exactly what we expected when I pulled a 4 inside of there. And then I have 4 in the bottom that's canceling out with the 4 in front of the km. So this is just k over m, like that. Okay, so that might seem kind of odd to you, but this is extremely important. Now I'm going to go back and say, well, x of t is equal to a e to the rho t. And what that means is I've got a times e to the negative b over 2m plus or minus square root of b over 2m squared minus k over m square root, and then all of this is times t. Okay, now that seems kind of weird, especially since I got a plus or minus, but it turns out if you're dealing with exponentials, a times e to the rho t is what we call linearly independent from a2 times e to the negative rho t. And that's a complete set. In other words, those two functions are enough to make essentially any function. So, and it's 2, which happens to be the same order as a differential equation. So what we often do is we'll say x of t is better suited by writing a1 e. Actually, let me write it a different way. I'm going to say I'll say a e to the negative b over 2mt. And that's just the part in front of the plus or minus. Notice if you have like x to the 2 times x to the, or excuse me, x to the 2 plus 4 power, that's the same as x to the 2 times x to the 4. That's what I'm doing here, but I'm going backwards. I'm taking x to the 2 plus 4 and breaking it down into x to the 2 times x to the 4. So in this case, I've just pulled out the negative b over 2m times t. But now what I'm going to do is I'm going to say there's another function c1, or there's another function that's e to the rho t, and then another function that's e to the negative rho t, but I'm going to add a couple constants in there. So I'm going to say c1 e to the rho t. In this case, I'm calling rho something different. I'm just going to take the positive sign here, and that's going to be the square root. And I'm going to do something funny here. Well, I'll do that next. I'll say this is just b over 2m squared minus k over m, like that, square root times t plus c2 e to the negative square root, the same stuff under the square root times time. That's a complete solution, but let me explain something to you. It turns out that if the quantity b over 2m squared minus k over m, so if b over 2m squared minus k over m is less than 0, then the square root of b over 2m squared minus k over m becomes I plus or minus, and this would be plus or minus as well. So this becomes plus or minus I times the square root of k over m minus b over 2m quantity squared, like that. In other words, I'm going on the assumption that b over 2m quantity squared is actually typically less than k over m. There's no reason to believe that, but there's a good reason for me to go on that assumption, because now I have this wonderful I, and this wonderful I can be used with Euler formula. The Euler equation is e to the I theta is equal to cosine theta plus I sine theta. Notice the cosine theta is completely real. Notice the sine theta is completely real, but when you multiply it by I, it's completely imaginary. So you can call this a solution, but you'd completely ignore the I sine theta if you wanted to. Or if it turned out, for instance, that b over 2m squared minus km wasn't negative, then you'd end up having the I on the different term. So that's another way that it can go. But the main thing that we see here is we definitely got in the x of t that I just wrote, I've got a e to the negative b over 2mt. That's an exponential decay. And now what I'm going to do is say that multiplied by c1 times e to the I something times t plus c2 times e to the negative I something times t gives me a cosine function, basically. So now that I use that, I can finally say x of t is equal to, let's call it a e to the negative b over 2mt. And then I'm going to say c1 e to the I square root of that stuff, t, plus c2 e to the negative I square root of that stuff times t. So basically what we get is a c1 and a c2 times each of those times a cosine function, and you basically get cosine of omega t. So I could write this as x of t is equal to a e to the negative b over 2mt times c1 cosine of, let's call this omega prime t, plus C2 cosine, and in this case, notice for Euler's formula, you also have e to the negative I theta would be cosine theta minus I sine theta. I'm ignoring the imaginary part already. So I just wrote the cosine part, and I get that. Just with the using just the cosine part times 2, there's really no need to have two different cosine functions. So I can just let C1 equal C2. If I really wanted to add some more freedom, I could add a plus phi inside the argument. But now you see I get x of t is equal to a e to the negative b over 2mt times cosine of the square root of b over, oops, we had written it the other way around, hold on. So this is k over m minus b over 2m squared times t plus phi if I wanted to. So this is just that phi that I said I like to add. Now, we had claimed the solution was x of t is equal to e to the negative gamma t cosine omega prime t. Now, again, adding this plus phi is completely up to you. I just happen to be a person that likes it. But when you're working problems in the book or the homework, they're going to assume that you're not using that. But now you can see exactly what gamma is. So we'll say where gamma is equal to b over 2m and omega prime is equal to the square root of k over m minus b over 2m squared, like that. And we still need two initial conditions. Okay. So that's basically how we do the damped harmonic oscillator. We just know the solution is going to work. We know that's what it is. But what happens if, for instance, I said, as they do in problem or in exercise 1414, I want to say, let's look at it. I am going to stop sharing my screen, and just for a second, I'm going to share a different screen. So let me stop sharing. And now let me share screen. And I'm going to share this one right here. So everybody sees what I'm looking at right now. This is example 14.4. They said a simple pendulum with damping. That's a big deal. That's not a simple harmonic oscillator with damping. So I don't have a K and an M necessarily. I don't have a B over M. I don't have a K over M. In fact, I'm not sure what I have, but what I do is the exact same thing that I just did, and that's the whole reason I showed it to you. So let me show what I do. I'm going to say example. Oh man, I hate it when I do that. I'm going to say example 14-14. Okay. Now, what I have is a simple pendulum. And what we decided for a simple pendulum was we'd have a ceiling like this. We have a vertical line to measure an angle with respect to. We have a line of length L with a mass m on the end, and that mass is a point particle. So for instance, the diameter is at least a factor of 10 smaller than L, so we can ignore the fact that it has any diameter whatsoever. And I'm going to say this angle right here is theta. I'm also going to say that this arc length right here is S, which equals L times theta. But I'm going to go further and say that this right here is the force acting, and it's mg. You can probably tell that it's going to have a component that's parallel to the string, and then it's going to have a component that's perpendicular to the string on the pendulum. This one is mg cosine theta, because I think you can tell that this is theta, and then this one is mg sine theta. So using Newton's second law, what we have is m d2s over dt squared is equal to negative. Now, this is basically not, this is not the equation for torque. We're just doing ma, and a is d2x over dt squared. And the force, which actually acts in the opposite direction of the angle theta, is going to be a negative, and I'm going to have mg sine theta. But since it's damped, I'm also going to add a minus b times dx dt. And if I allow, so let's assume sine theta is approximately equal to theta. If I do that, we can see, I'm going to divide through by m first. We can see that d2 L theta, because that's what S is, over dt squared plus g theta plus b over m dx dt is equal to 0. That's not really in the form that we like it. In fact, what I'm going to do is I'm going to pull that L out of the second order derivative, and then I'm going to divide everything by L, because the L is just a constant. That's why I can pull it out of the derivative. So next I'm going to get d2 theta over dt squared plus b over m times L dx, or excuse me, d theta dt. I don't know why I said dx dt. Oh, actually, I should say L d theta dt. Sorry about that. Let's go back. I want to fix that real quick. And this right quick. Remember, we're talking about a velocity, which is ds dt, dl theta dt. So in this case, this was b, whoa, Nelly, did not expect that. This was b times l d theta dt plus g over l theta is equal to 0. You can see the L's drop out here. So it turns out that finally we can get our damped harmonic oscillator equation is d2 theta over dt squared plus b over m d theta over dt plus g over L theta is equal to 0. And this is our damped harmonic oscillator, and we need two initial conditions. Okay. I think you can probably tell that basically what we're going to get is theta is equal to theta 0 times e to the negative b over 2mt times cosine of, now in this case, it all depends on what you want to do, but it's probably going to be g over L minus, actually it's probably going to be No, it'll still work out that way. G over L times B over 2M quantity squared times T. And again, plus or minus phi. You might have that or might not, but that's the main thing. So that's how we go about solving that one. So notice how just by putting in that derivative stuff, we can figure out exactly what the functions are. So I got b squared over 4m squared, and I got g over L. And I think that's about it. Oh, okay, I see they did theirs a little differently. They chose to do it at, well, no, they still chose to do it the same way, but they absorbed one of the L's in their B. I didn't do that. Technically speaking, this B should be a velocity, or B times a velocity. So that's something with meters per second. That theta has units of radians, and d theta dt has units of radians per second. So that doesn't work. So that's why my formula slightly differs from theirs, but they're completely compatible. So anybody have any questions on that? All right, so that little process of getting that algebraic equation, notice this was the algebraic equation. I'll put it in a bright box. This equation, right? Oh, that is not very impressive of a box. Let me change colors. This equation is an algebraic equation, and it's called the characteristic equation. Okay, and that's what allows you to figure out what omega is, what gamma is, all that good stuff. So just always consider doing this part right here, and you can get that characteristic equation and then use the quadratic formula to figure out what the exponent of E is. And then notice there will be a part that has the potential to have an I in it. That's the part after the plus or minus. And then there's a part that's just a exponential decay. That's the negative B over 2M. That's where you get the negative gamma T. So when you look at, for instance, a damped harmonic oscillator, the output looks like a sine, but in this case, its amplitude is exponentially decaying. So these little dashed lines are basically plus or minus 1 times e to the negative b over 2mt. So that's what causes it to be damped. And in this case, it's called underdamped. Your book takes the time to show you the 3 scenarios, but he doesn't give you all the details. If you take in actual differential equations, you get some more of the details. But this one B right here is what we call underdamped. And the reason why it's underdamped is we actually have a sinusoidal wave. So this is more like, say, the hinge on a door to a kitchen in a restaurant. When you push the door open and walk through, the door swings back past close and then swings back past close again the other way. And then, of course, it's a smaller amplitude each time, and then past close again, and then past close again, and then past close again, and then it just comes to a stop. That's underdamped because it made many, many cycles, and that occurs for some very specific results. So, for instance, what I'm saying here is underdamped implies the square root of k over m minus b over 2m squared. Actually, I should say it the other way technically. So let me say, yeah, let me erase this. I'll do it this way. So we originally had basically a b over 2m squared minus k over L, like that. Was it k? No, it's k over m. Sorry about that. over K over M. And we assumed that was going to be negative. And in fact, what overdamped is this is actually less than 0, so that the square root of B over 2M squared minus K over M became I times the square root of K over M minus B over 2M squared. That's me fitting it in too small of an area, so I really should not do that. So I'll say this actually implies that the square root of B over 2M squared minus K over M with a plus or minus in front of it, that ends up being plus or minus I times K over M minus B over 2M quantity squared, which gives you basically X. Did I do X or did I do theta? Yeah, I did X for the original. So it's X is equal to A e to the negative B over 2MT times cosine omega prime T, where this quantity is omega prime. So does that make sense? So that's the underdamped, and that's the omega prime, and that's our gamma. So this quantity B over 2M is equal to gamma, and that quantity, which I said is the square root and everything, that's omega prime, and I'll put that in red like that. Now that's the underdamped case, and that corresponds to a graph that looks like, let's say this is our x-axis, and let's say this is our t-axis, and that would look, by me adding a plus phi, I could actually get some changes where this wouldn't start here, but without the phi, you basically have to have a function that looks like this. Where what we're looking at here is a series of exponential decays that are being multiplied by a trig function, and therefore we end up getting a plus or minus exponential decay like that. So that's underdamped. If I go now to overdamped, if I go to overdamped, what that means is B over 2M quantity squared minus K over M is actually greater than 0. So what you end up getting is X is equal to A times e to the negative B over 2MT times e to the square root of B over 2M squared minus K over M, and this will be the plus one, times T, plus, let's say, some other constant, which I could have put in there. Let's say C1 e to the negative square root, exactly the same square root, basically, times T. But in this case, the two e's are not linearly independent. Actually, they are linearly independent, but they're not. They don't have an imaginary number in it, so you really don't get necessarily any kind of trig function oscillating back and forth. But the graph in this case just looks like this. There's T. There's my x-axis, And in this case, this is called overdamped, and the motion would look basically like that. Okay. So it doesn't have the ability to oscillate back and forth at all because there's no trig functions in it. Any questions on that one? Again, this should seem like really obvious stuff if you've already had differential equations. If you haven't had differential equations, it could be quite confusing, but the important thing is you don't have to think about any of these details. You just have to write down the answers like the author gave you. So the last case is critically damped. And critically here means something very specific. It means that the square root is 0. So that's a problem, but that's what we're going to do here. This is critically damped. Dang it, I hate this. Critically damped. And critically damped basically means that b over 2m squared minus k over m is actually equal to 0, which means rho is only equal to negative b over 2m. And you could, just to express it, you could say plus or minus 0. So that's not very helpful. It's not necessarily the right type of function. And in fact, if you want to establish what the right type of function is, you need two linearly independent functions. And to do that, what you ultimately do, and your book makes no comment about this, so I'm just telling you for completeness, you can just completely follow the instructions that your problem gives you. But what this is going to become is you're going to say x of t is going to be a times e to the negative b over 2m times t, and it would be times e to the 0, but we don't have an e to the anything other than e to the 0, which is just 1. So that doesn't mean it, that's not helpful. So what we end up having to do is we multiply it by a second order polynomial. If it was a third order differential equation, we'd multiply it by a third order polynomial. So what I'm going to do is I'm going to say C1 plus C2t. There's my second order polynomial. That's actually what that function is. And that's actually the solution to this equation. If you take this, take its derivative, take its second derivative, plug this all in, you will find that it does solve that differential equation. And you will find that this has a graph that looks like this. So here's our x, here's our t. In this case, it doesn't look very much like anything. In fact, it goes, well, actually, I should probably do it in red like I've been doing before. It stays high for a longer time and then goes on like this. In fact, it might even look a little bit more bumpy than this one, and the other one looked a little more decayed. But either way, that's basically what we're trying to show. So let me say something like this. Okay, so that's critically damped. But the main thing is you need to be able to know what conditions on B, M, and K, for instance, give you damped, critically damped, and overdamped or underdamped, excuse me. So that's all. You don't have to actually write these different functions out and everything, but you should assume that in general, your solution's always of this form down here with the blue underline. Whoa, Nelly. So let me kill this sharing. Let me share another screen. Go back to my iPad, share. Okay, so I wrote a few things and I need to catch up to speed with what I wrote. So we had reached the conclusion, once this comes up, this should help us. We had reached the conclusion that for a damped harmonic oscillator, the equation that is a solution is this, and that's what your author is going to expect you to use over and over and over again. But like I said, what I just explained to you was this was in fact not really the solution, not for the critically damped and not for the over damped case. I'm trying to fix this, by the way. There you go. Okay. What happened was for the underdamped case, we got this top box, and I showed you that what was under the square root did actually come out to be negative. So you can flip the order and multiply the square root times an I. That allows you to see that you get e to the I theta, which gives you that cosine term, and it gives you that exponential decay term. So you can immediately see what gamma is. Gamma is b over 2m. And you can immediately see what omega prime is. That's the square root of k over m minus b over 2m quantity squared. That's the underdamped case, and this is the condition. Actually, let me just erase that. That looks horrible. So this is the condition for overdamp. Okay. Now, if you look at this, you see this right here is the overdamp condition. So you can, take your K, take your B, take your M, and evaluate B over 2M squared, evaluate K over M. And if you see B over 2M squared is bigger than K over M, then you know it's an overdamped case. And your solution is going to be this, which again, your book didn't tell you anything about, so you really don't need it. All you need to know is that condition is what's necessary for the graph to look like this. And then the critically damped has B over 2M quantity squared is going to be actually equal to K over M. And this is the actual solution. But again, your book didn't give you that. So evidently you only need to know the condition, which is that. Any questions on that? All right. So that is the majority of what's left. Now, there's also another condition. What if, in addition to all that junk, you had, let's say, d2x over dt squared plus b over m dx dt plus k over m x. But instead of it being equal to 0, what if you had f0 cosine omega 0 t, like that? Well, that could be a real nightmare, and this is called a forced, forced damped harmonic oscillator. Now, the good news is it turns out in differential equations, you learn that when you have a linear homogeneous equation, that's basically the left-hand side that I've written here, equal to 0. And this part right here makes it inhomogeneous. So this is inhomogeneous. And what the theorem tells us in differential equations is that if you find a solution for the homogeneous case, then the solution for the inhomogeneous case, once you find that, you can just add it to the homogeneous case, and that'll give you the solution of the inhomogeneous case. So if I jump forward to section 14.7 actually, I think it might be 14.8. Yeah, if I jump forward to subsection 14-8, then what I can see is I get the forced harmonic oscillator, and we'll see, for instance, the Tacoma Narrows Bridge or the horrible earthquake that happened in 1989 during the World Series. And then we can go a little further to subsection 1, and what they tell you is that the function that answers this is x of t. This is the solution. Is x of t equals a sine omega t plus phi, okay? And you might guess exactly what omega is. Omega is going to be that same function we had before. So omega is going to be the square root of, let's say, b over 2m. No, actually, we did it the other way around. So it's going to be k over m minus b over 2m squared. And it turns out for this particular case, you can have A, the amplitude is going to be equal to F0 over M times the square root of omega squared minus omega 0 squared times the square of that, or basically squared that, plus b squared omega squared over m squared, all of that being under the square root, and phi is going to equal the inverse tangent of omega 0 squared minus omega squared, all of that over omega times b over m. Okay, so that's it. You don't have to do anything. You don't have to think about anything. If you want to, you can confirm that this does solve the equation. That's great. That would be an excellent exercise for you. But you just need to know, hey, if this is the equation, then this right here is the solution. Okay. Any questions about that? All right. What you can see here is, notice if omega is equal to omega 0, see the omega squared and the omega 0 squared? If those two are equal, this term, this first term under the square root in the amplitude becomes 0, and the amplitude gets really, really big. That's called resonance. So that's called resonance. And it means the amplitude increases greatly. And there's a quantity that measures how good that is, and that quantity is called the Q value. And the Q value is actually equal to Q, which is in fact m omega 0 over b. And what we find is for very large Q, we have a very large amplitude, and for very small Q, we have a very small amplitude. So Q large implies a lot of resonance such that A gets large. But when it's small, say on the order of, say, 1 or 2 or something, then little resonance. Such that A does not get very big. So the perfect example of this is, you don't have to actually have a mass on a spring. We just showed you how you can have damp motion for a pendulum. So imagine a little kid runs out to a swing set, jumps on the swing set. Now, if the kid's got any kind of rhythm or any kind of experience with swings, what he'll notice is when he kicks his leg forward, the swing slides back a little bit or flies back a little bit. And then when he pulls his legs back, the swing goes forward a little bit. And if he does that just right, he can force himself to speed up, speed up, speed up. So as close as he can get that force, which we called F0 cosine omega t, or cosine omega 0 t, as close as he can get that to the omega that's natural for the B and the K, or excuse me, the B and the G over L and all that good stuff, then he starts to approach a resonance so that he can get higher and higher and higher. And in fact, I saw a kid do this one time while I was sitting at the elementary school waiting to pick up my daughter. He just come running out like some kind of crazy person. And not only did he jump on the swing, he jumped on the swing standing up. So his feet were on the platform as opposed to his butt sitting on the platform. And he was holding on to the chains, and he leaned back real far, and that made it go up real high. And he leaned forward real far, and that made it go real high the other way. And he kept going. Next thing you know, this crazy little nut flips completely over upside down. I'm like, oh, this guy's like a superhero. He's like the most impressive thing ever. And I'm really excited because that is exactly what I always wanted to do as a child, but I never had the guts to just try it. So he does this. And what he did was he actually worked out resonance so well that he could loop around the swing set a couple times. Now, if you come and take, let's say, a moronic child or a moronic person, and they just go out there and they just randomly kick and swing their arms and legs in random directions, then you're going to get a very low Q value because the resonance is very unlikely, and you're not necessarily going to get the swing to go up and down. So that's a good example of resonance versus not resonance. Anybody have any questions on that? All right, so we've finished essentially chapter 15. What you should be able to do is you should be able to look at functions. Like if someone says, let me give you an example here. Let's say someone gives you an example, x is equal to 0.143 meters times cosine of 377 t, like that, then you should be able to tell me what is A. You should be able to tell me what is F. You should be able to tell me what is omega, what is the period, all that good stuff like that. Anybody have any questions on how you do that? Hopefully y'all do know that. I've sort of hinted at it in the past and done a few examples. Do y'all know what to do? Can anybody, for instance, tell me what A is? Anyone? Anyone? So A is 0.143 meters. Omega is 377 radians per second. Omega also is equal to 2 pi times F. So that means F is equal to omega over 2 pi. And you'll see that F is in fact equal to 60.0 hertz. And then the period T is equal to 0.0167 seconds. So that's a key skill that you need, and it's one of the most important skills from chapter 14. Now we move on to chapter 15. And what I need you to know is what a wave equation is. So your book talks a little bit about wave motion. It talks about crests and troughs and amplitudes and wavelength and all that good stuff. So I want to do that as well. But you can imagine a wave is a disturbance that repeats itself in space and in time. So those other things just repeat themselves in time, the stuff that we did in chapter 14. A wave repeats itself in space and time. So you can look at a wave, for instance, like this. You can say, here's X, and here is T, and we'll say, like this, and the smallest distance over which it repeats itself, let's say from here to exactly the same spot here, that is, since we're measuring it in time, that is the period. Okay. And this distance right here is called the amplitude, but so is this distance. And I didn't draw this perfectly symmetrically, so just remember they're supposed to be equal. Now, if I also draw, I probably shouldn't have made that an X. Let's make this, instead of an X, let's make it a D. And now I'll make this as a D and this as a X, so we know it's space. And in this case, this might be the same wave, by the way. In this case, and this is supposed to be a perfectly sinusoidal wave. Clearly it's not, right? So in this case, what you can say is, let's go back to black. I can say from here to here, that is the wavelength. That's the minimal distance in space that it repeats itself. But I could also say it's from here to here. And that's typically measured like in meters. So T has units of seconds. Amplitude could have units of meters. It could have units of newtons per square meter. It could have units of kilograms per cubic meter. Basically, it could be anything. Like a pressure wave would be newtons per square meter. Ocean wave, the amplitude would be the height, so that's why I put the meter on there. A sound wave is a longitudinal wave. That's one that vibrates in the same direction that it propagates, whereas a transverse wave is one that vibrates perpendicular to its motion. So that's a transverse wave. In this case, we've got all of these quantities that are listed here. So lambda is the wavelength. And as I said, in that case, lambda would have units of meters. Again, this is also the amplitude from the midline up and the midline down. Those are the amplitudes as well. But that's the parts of a wave. So it's actually going up in time, but it's also moving. It's moving forward in time, but it's also repeating itself in space. Okay. And the equation for a wave is called a wave equation. And this is the grown up wave equation that you know from differential equations. And for instance, you could say the amplitude is given by d of x and t, in which case you'd say the second derivative of d with respect to x squared is equal to 1 over the velocity squared times the second derivative of d with respect to time squared. That is the wave equation. Okay. And it turns out that it has solutions of the form d of x and t is equal to some amplitude times, I think your book is choosing to use sine on this one, so let me double check just to make sure. I'm flipping through chapter 15. I think it's using sine for this one. Oh, I also should say that's a crest, and that is a trough. Okay. You could also say, of course, from trough to trough is also a wavelength. Okay, so that's another sign. I'm looking again just to double check. I think they're using sine here. Let me see if I can find it. That's not it. I just want to double check. I've got plenty of time, so it's not a big deal. Let's do the next one. Let's do the next one. That's not it either. That's not it either. Still not it. Okay, this is really helpful. There it is. So they are using sine. So what this turns out to be is A times the sine of, now this part's a little weird, you might not recognize it. It's k times x minus omega t. And this is called a plane wave. And what a plane wave looks like is, you might imagine it looking like this. And then what that means is over here, we're going to have the same function like this. So this one's going to be that way. This one's going to be that way. This one's going to be that way. That's going to be that. That's going to be that, that, and that. What I mean by a plane wave is, in fact, you can make a plane that's this way. In other words, perpendicular to the direction that the wave is actually going. The wave, by the way, is traveling, say, this way. Now, this plane will intersect this wave right across this one spot, and that shows you that the value on a single plane of this wave has a single value. In other words, this one I happen to draw right at the crest. So the crest has a value of A, and the whole wave has a value of A on that whole plane, and that's why they call it a plane wave. Now, what I'm going to tell you is this right here is called the phase, and it corresponds to one of those values. So, for instance, it could be equal to 2 pi. So you could say 2 pi is equal to kx minus omega t, or you could just call it, let's say, phi, for any number you wanted to. But if I did 2 pi, then I'd know that I'm looking specifically in the sine wave, I'm looking for a point where it's 0. Or I could say, let's say it is 0, or I could say it's going to be 2 pi, or let's say it could be -1 or something weird, or actually not -1, but it could be just plain pi. All of those are potential values, but the main thing is a constant. So I'm talking about one spot on a wave, and what I want to do is see how that spot on the wave moves as a function of time. So I'm going to solve it for x. And what I get is x, which I can pretend like is like a function of time. I'm going to say x is in fact equal to, I'm going to take the function kx minus omega t. I'm going to put the omega t on the other side. So this is going to be omega times t. But then, of course, since I'm solving for x, I got to divide through by k. And then I also have the phi that's there already. So that's going to be phi over k. So what you can see is at t equals 0, x of 0 is equal to just phi over k. But at x of 1.0 seconds, I get that phi, excuse me, I get that x is equal to omega over k times 1 second plus phi over k. So you see that this particular phase implies moving in the positive direction. If you had phi is equal to kx plus omega t, that's going to give you x of t is equal to negative omega over kt plus phi over k, and that means it's moving in the negative direction. Does that make sense to you guys? Y'all see how that works? Now, if you look at your kinematic equations, do you have any kinematic equations that give you x is equal to something times time plus something with units of meters? Y'all remember a kinematic equation that looked like that? And by the way, this has meters as well. And obviously this has a very specific unit. So anybody want to tell me what kinematic equation looks like that? That was just this semester. So the kinematic equation that looks like that is just x is equal to x0 plus vt, or you could say vt plus x0. So it looks just like that. And that's exactly what this function looks like. So you might be able to glean from that when you say x of t is equal to omega over k times t plus phi over k, and you see x is equal to vt plus x0, you might reach the conclusion that v is equal to omega over k, and you'd be exactly right. So v equals omega over k is true, and here's where I'm going to define omega. We already know to some extent omega is 2 pi f. It turns out k is supposed to be just like omega, where omega is a representation related to time and k is a representation related to space. So k is actually 2 pi over the wavelength. To make omega look more like that, you can replace the f with 1 over t, and you get 2 pi over the period divided by 2 pi over the wavelength. And you can see in this case, the 2 pi's cancel out, and I get, in fact, lambda over t, which is a wave equation, but it's not the one I'm used to using. So what I ultimately reach the conclusion is that v is equal to lambda times f, or v is equal to lambda over the period. Either one of those are acceptable, and they're called our baby wave equations. Okay. So if you know two values, if you know the velocity and the wavelength, or the velocity and the frequency, or the wavelength and the frequency, you can solve for the other one. So a typical example that I want you guys to be able to do, this is, it's right at time for class to be over. So I'll say one particular example is, what is the wavelength for AM 850? And I'd say, what is the wavelength for FM 93.7? Okay. Those are typical questions. Now, what you first got to ask yourself is what type of wave they are. So, what type of waves? Can anybody tell me what kind of waves radio waves are? So they're not sound. I'll give you that as a hint. And radio waves are, in fact, electromagnetic radiation. And radiation just means it's radiating outward. It doesn't mean, ooh, I'm going to get, radiation poisoning, anything like that. And that means that V is equal to C, which is 299,792,458.0 with an infinite number of zeros after it, meters per second. That's the velocity. So with that in mind, I only had to give you that one quantity. So what we find out is lambda 850 is equal to, looking at our wave equation, lambda is supposed to be v over f. So I'm going to say that's approximately 3.00 times 10 to the 8th meter per second. Notice I've just rounded it to 3 sig figs. That's going to be divided by the frequency. And the frequency for 850 AM is 850 kilohertz. So I'll say times 10 to the third hertz, which gives me about 352 meters. lambda 93.7 is actually 3.00 times 10 to the 8th meters per second over, in this case, it's 93.7, but it's megahertz, so it's times 10 to the 6 hertz. And that gives me, I want to say 3.201. And that's it, okay? If I said a wave had a wavelength, we'd say, what is V for a water wave where lambda is equal to 20 meters and frequency is equal to 0.25 hertz. Then velocity is equal to frequency times wavelength, gives me 20 divided by 4, which is 5.0 meters per second. Now, what your book did give you, and we're free to go, everybody, but the one thing I want to tell you is that the velocity for a wave on a string is the square root of the tension divided by the mass per unit length. And this is the tension. And your book gives you other formulas too. It gives you like velocities equal to the elastic modulus over rho. That's for a rod. So a wave traveling down a rod. Our velocity is equal to the bulk modulus over rho. So that's in a liquid. And so on and so forth. I'll leave the rest up to you. The rest of it's just concepts. I might post some videos between now and next time that might help you a little bit, but I think that's plenty good. You should be able to now, just like I did before, look at a function, and just like I did with that phase, you set that phase equal to, say, 0, and then solve it, and you should be able to figure out what the omega is, what the K is, what the velocity is, all that good stuff. So you guys are free to go. I'll wait for the last person to leave in case anybody has any questions. But thank you for coming, everybody. Remember, you got an exam right after this on Tuesday. If anybody wants to take it some other time, you might be able to. I'm going to allow you to take it with the Respondus lockdown browser and the Respondus monitor. Otherwise, you'll have to take it at a testing center or get someone to proctor it for you.
So just to clarify, we can take it at home as long as we have Respondus and a camera?
Exactly. Yep. You just need to make sure you have a camera and I can get a good view of you, that sort of thing.
Gotcha. Thank you so much.
You're welcome. Thank you, Gabrielle. Michael, Logan, Alyssa, go ahead, Alyssa.
What time today?
What
Could
was
you hear
that?
what I said? I'm sorry.
No, I talked over you. I'm sorry.
I was saying, what time is it on Tuesday, you said?
You're supposed to take it. I think your lab class starts like 30 minutes after class is over. If you take it, if you start a little late or a little early, I don't have a problem with it. I just don't want you to be more than, say, 30 minutes late. I don't want anyone to have the chance to finish the test, talk to you about it, and then you take the test. So as long as you're not more than 30, 45 minutes late starting it, that'll be fine.
So we do it in the lab?
You do it at home anywhere you want, where you have a reliable internet connection and you have a computer that can run Canvas and can run the Respondus lockdown browser and Respondus monitor. So you can take it at home, you can take it at the library, whatever's best for you.
I just wonder, I'm sorry, is it Monday or Tuesday?
Oh crap, this is Wednesday. Thank you. I was making the mistake. I was thinking this was Thursday. So yeah, it'll be Monday, not Tuesday. I'll send out an email to clarify that in case anybody misunderstood me or actually understood me.
All right, Monday, sorry.
Yeah, sorry about that, Alyssa.
Okay.
Logan, do you have anything?
Yeah, you answered the question. I was just gonna ask if we could take it at home, but you answered that. So
Yeah, I think it's just easier for you guys. As long as it doesn't look like people are taking advantage of that, then I'll continue to do it. But if I find any other problems, like sometimes I have people that you can just tell they're cheating, and if that
yeah.
ever comes up, I'd have to do something. But so far, you guys have been really good. I'm sure you're not going to cheat.
Yeah, it's just a lot easier for me because of the distance, but
Yeah, I
okay.
feel you. I live in North Carolina, so I feel you.
Oh yes, it is a struggle. But I appreciate it.
You're welcome. You have a good one.
Thanks, you too.
Bye bye. Alyssa, do you have anything? Oh, she's gone too. All right. Looks like everybody is happy-go-lucky. I will tell you guys that you definitely need to go over and read material in the chapter about interference, about standing waves, about resonance, harmonics, fundamentals, the first harmonic being the fundamental, and the second harmonic, and then the third harmonic and the fourth harmonic for standing waves, refraction, diffraction. And the interference is really important. Specifically, make sure you read reflection and transmission, which is section 15.7, principle of superposition, which is 15.6. The wave equation is always going to look like that. A second order derivative in space is equal to 1 over v squared times a second order derivative in time. And the thing that you're taking the derivative of is the amplitude. If it's traveling along in the x direction along the positive x-axis, the positive x-axis in the positive direction, then the argument of the sine function is kx minus omega t. If it's moving in the negative x direction, the argument is kx plus omega t. If it's moving along the y direction, the argument is ky minus omega t. If it's going in the positive direction, or ky plus omega t in the negative direction, or if it's moving in the z direction, it's kz minus omega t for the positive direction, or kz plus omega t for the negative direction. Or more generally, you can just say that the argument should be like k sub x times x plus k sub y times y plus k sub z times z, assuming it's going in the x comma y comma z direction. In other words, if you draw a line from the origin to the point xyz, it's going along that line, and the kx part would be replaced with k sub x times x plus k sub y times y plus k sub z times z minus omega t. So that's how that works. That's what the direction of the oscillation is. The velocity, of course, is along the x direction or the y direction or the z direction or the xyz direction, whatever. So that's all your mathematical stuff that you need to know. There's a picture where they show a pulse on a rope running over another pulse. You should understand that. There's a picture where it has a pulse on a light rope running into a heavy rope, or a pulse on a heavy rope running into a light rope. All of those things are things you should know. And I especially say that because I one time co-authored a book for preparing for the MCAT and the LSAT. Both of those had those types of questions on them for physics. So definitely look in reading all of chapter 15. I think doing the practice test will give you good help, but make sure you ask me questions if you have them. Bye, everyone. Bye.